Welcome to the salt and water management session. As Paul noted in luncheon, this came to be about 8 years ago. And actually, the way I feel, the real award was 8 years ago because I was handed a project that enabled I to work with my esteemed colleague Andy Franz and bring a lot of things together into one tight package. So this is kind of the capstone presentation of this project. And our first speaker is Dr. Franz, and he's going to try to address the water issues.
Well, thank you. Good afternoon. Wonderful lunch. What I'd like to do is present really a story in 3 parts. One is a summary of the findings of this report that Sonnet and Charles just mentioned. And the second part is to go into a little bit more detail on how the data were acquired, to give a little bit of credibility and understanding of how those data were collected so that you can understand and explain to others that these data are good and meaningful. And the third part is our new directions, which include a couple additional crops not covered in this report and some ideas on predicting water use. So first, of course, none of this would have been possible without collaborations. And Dr. Sanchez has been absolutely critical for the success of this project, and I thank him a lot for bringing him into this project in 2016. And I also have to thank other organizations, USDA, my former employer. Bureau of Reclamation has made major contributions to the effort and the study. We've also had, since the initiation of the study, we had collaborators in Riverside, California, both at UC Riverside and USDA Riverside, Salinity Lab, which you probably know about, and more recently with Arizona State University with some work using commercial satellite data. So here's a summary of the study. The copy of the report is over there on the table. Many of you have already read it or looked at it. What did we do since 2016? Well, we did a lot. We looked at many crops, 14 key crops, 5 of which had direct comparables from years ago, decades ago, and I'll explain a little bit of that later, and 9 of them with no direct comparables. Some examples of how the water use changed for that is like for broccoli and cauliflower, the estimates of water use decreased from those previous estimates. In the lettuce, water use increased a little bit. It doesn't look at yield changes over those decades, it just looks at the consumptive water use. A key takeaway from this report is that water use efficiencies in Yuma are very high. The gravity-fed irrigation systems are subject to a lot of criticism and misunderstanding, and what we have found is that those irrigation efficiencies are typically in the 80 to 90%, which is extraordinary. In fact, probably can't be increased further because of the need to regulate salinity, as Dr. Sanchez will explain. And thus, this report takes a first look at the efficacy of current irrigation practices versus proposed alternatives by other outsiders maybe, or sometimes insiders for drip irrigation. We looked a little bit at the consequence of fallowing, which is something I know that's been done in California, maybe not in Arizona that I'm aware of. And what we found in those results was that those fallowing exercises can harm the soil health after you want to bring them back into production. So the water savings effect of that are immediate maybe, but long-term, those savings go away because you have to remediate those fields. So we're not saying you shouldn't do it. We're saying is you have to be cautious because you could have a cost on the back end. So what we did in this report is we updated the salt balance and salt management recommendations, identified salt loading events, which I won't go into here. That's Dr. Sanchez's territory. And we highlight the importance of pre-irrigation. U.S. brick irrigation obviously has a major relevance for this area. They want to know how much water is being consumed and how much water is being returned to the Colorado River. And they have an accounting system that they come out with mandated by Supreme Court from the early 60s. And they also have a secondary report called evapotranspiration report, which is badly out of date. I think the last is 2016. Last I checked, this is 2024. So they're pretty badly out of date. But they have an evapotranspiration report where they go down crop by crop and they report on how much water each crop uses. And they have an evaluation system based on a 2003 methodology based on Marv Jensen's work, who's a very well respected and known scientist of his day. And what we've done is we've adopted new technologies with satellite data to improve those water use estimates. So what we do in that methodology is we're testing and evaluating the use of satellite data to improve the water use estimates in each individual field as opposed to aggregate irrigation districts. Lastly, and that will be the final talk of today, was we're developing a couple of apps that will be easy to use. One will be an irrigation and salinity management app, and the second will be a crop coefficient map. Maybe Dr. Sanchez will describe that a little bit. Here's the nitty-gritty. The numbers are all in the report, but I think it's more effective to show a graphical layout of how much water each crop uses in each growing season. Here's a box plot. I plotted in inches per growing season, and they're ranked. So on the bottom there is obviously spinach, which is a very short crop, all the way to cotton alfalfa. Alfalfa is a very important crop that we're not finished studying yet, so I'm not plotting those. Everything in the blue boxes there are data that we collected. Everything with the red dots are from Leonard Erie's 1960s and 70s studies. And what those are used to show you is, first of all, that our numbers are fairly well alignment with those studies, so it's an independent validation of our work. And secondly, to show you there are some major differences. For example, with you can see the red dot above cantaloupe and iceberg and cauliflower have some deviations. Our data is different from his. I mentioned this morning, some of you might have been here in this, there's a competitive consumptive water use product known as OpenET. It's being promoted a lot by NASA and USGS and other organizations. It's being adopted to some extent in the state of California. I'm not aware of what agencies are considering serious adoption of it or not, but it's an online tool that provides water use estimates daily, but actually based on monthly estimates. And it's a remote sensing data product, everything from the west of the 100th meridian. And I mention it because we've looked at these data too and compared OpenET results with ours, and you can see the results. Our results show, primarily for vegetable crops, but also for cotton and alfalfa, is that the OpenET are not very accurate. So I highlight it because people need to know that OpenET is a worthwhile and important product, and it will be mentioned a lot in the literature and public discussions, but it might not be accurate, and it needs to be discussed. Our findings in UMA are different from OpenET, and you can see that those results differ quite a bit. Some of the things that we weren't able to put into the report, but go behind the report and are available to anybody that happened to be interested. Here's some results for lettuce. Just 2 days ago, our key manuscript on lettuce was accepted for publication, Irrigation Science, and some of those results are presented here on the slide. On the upper left shows you the 12 lettuce sites, which is a rather large selection of eddy covariance deployments we used. Most sites were fewer. But what you see in the red curve are the Leonard Erie estimates from the 1960s, which are, I would say, they were good data at the time, but the black shows you what actually happens here in Yuma. And it hardly needs to be said that the red and the black do not agree very well at all. It shows it's really important to actually go out there in the field and measure it, not just with instrumentation, modern instrumentation, but in the locale that you have. Also shows that there's a lot of early season evaporation that the Leonard Erie model didn't do. But oddly, the Leonard Erie model still, I guess, comes up with mostly the right answer, 8 inches versus 10 inches for lettuce, but but maybe for the wrong reasons. There's some details here I won't read on the right in the table, but part of the point is that the early season evaporation is around 30 to 40% of total consumptive water use, and that therein lies the opportunity to save water should you wish to do that. We've been looking at heat units to improve the estimation of water use before you go into the ground, or if you're doing some forecasting. And those curves down at the bottom show you the estimates for the heat units and growth stages at different planting dates. So on the lower left, you can see the DOP, which is data planning, and you can see the growth stages, which are labeled LN, LDEV, and the total just means the length of those growth stages, and they highly depend on when you plant. Most of you probably know that, but what we've been able to do with these data is to quantify that much more precisely than it's done in literature. We've taken that data and heat units, and we've projected that into actual water use, which is the curve on the right-hand side, and shows you how the total consumptive water use reaches a minimum. All right, well, let's see, it's day 280. So not at the shortest day of the year, but if you plant, say, in October, you would have a minimum water use. So all those data can be accessed from data that we have, not necessarily in the report, but we'd be glad to provide it with you. As I said at a meeting last week, the work that goes into the numbers that you see in that report was huge. I mean, the amount of labor and team and effort in the middle of the night, all days to place eddy covariance was huge. But I used to have a former boss who says, I don't care how hard it was, what'd you find out at the end, right? Well, we found out a lot, and I'll show you. But here are the deployments. You can see all the crops listed. We started in summer of 2016, and the chart goes down to 2022, but we're still active. We still have citrus and alfalfa studies. What do the data look like that we analyze and maybe not always present to you in the report? They look like these charts on the right-hand side and bottom left, in the bottom row. There are three predominant colors. Black are the actual daily evapotranspiration values that we get from those deployments. The red is reference evapotranspiration, which you can get from Arizona weather stations or gridded weather data. And the purple is the vegetation index from satellite data. And the reason we include that is that it's correlated or not correlated with water use. And it's also independent of the time of year. So if you look at each of these crops, for example, I'll highlight celery, which is in the upper right-hand corner. You can see that the water use, the black curve, decreases down to the shortest day of the year and goes back up. But the NDVI curve, which is the purple, increases a maximum about the same time. Well, what's the value of that data? The value of that is when the biomass changes and when the maximum cover is independent of the total water use. Along the bottom, we can track the irrigation events, which we know. So we can correlate the daily evapotranspiration versus those irrigation events, and we know the irrigation types. So a little bit of the methodology, and know that there's competition and techniques. Well, the oldest, of course, is Leonard Erie's approach, which was gravimetric sample. You go out there, you collect a sample, weigh it, try it, weigh it again, and look at the water that's been lost. Very accurate, very time-intensive, labor-intensive, and in the end, what do you have? You have a core sampled from somewhere in the field, but if you've got a 40-acre field, how do you know that's representative? So a very good technique. Leonard Erie came up with some really very good numbers. This is what he has for lettuce. Well, it's kind of crude. It's good data, but if you want precise data, this isn't your method. Another good method that I was part of until I retired last year for USDA is neutron probes. And the neutron probes allow you to measure the soil moisture content at multiple levels throughout the growing season. An excellent way to measure the migration of the root zone and the soil moisture throughout the day. Very intensive, time-intensive, labor-intensive. You have to use a Giddings to install the probes. So good technique, good research technique, but not good for production agriculture. Another method that's been around for years is Bowen ratio, which is a stripped down version of what we used. It's essentially a ratio of sensible and latent heat flux. A very simple station is shown on the lower left, and the mathematical equation is lower right. The beta term is what you call the Bowen ratio. It's just the ratio of those of the sensible and latent heat flux. Rn and G are just radiation and energy that goes in the ground. Le is what we want for water use. Good method, but biased. Weighing lysimeters is probably the gold standard if you really gotta know exactly what the water is. Weighing lysimeters are a tremendous piece of equipment. The only one that I know of that's of large magnitude and really reliable is out in Bushland, Texas. It's expensive. It's probably difficult to install them. I mean, when they're monolithic, they take out the soil that's there, but preserve the soil profile. They preserve everything and then put that back into the lysimeter and they weigh that. I'm not sure the weighing interval, it's probably every 10 minutes. So you know exactly the inputs and outputs. Great technique, but the experimental protocol is difficult. So a gold standard if you can afford the effort. Another method that I mentioned, and not gratuitous, is the weather station. It's not gratuitous because we use that for later estimates. Essentially what you're doing is something like Arizona weather station data. It gives you reference of evapotranspiration. These weather stations are needed for everybody, and they're widely available. And you can integrate them with crop coefficients, which are also readily available for most crops. It doesn't explicitly model evapotranspiration. So for our study, it was not good enough for the validation that goes in the report. Now, there are other techniques you might hear of. Quite popular, I think, commercial companies in California. I've done some work with them. They're called flux variance and surface renewal, and you can buy such sensors and deploy them out in your field. I'd caution you against using those if you are tempted to deploy them for accurate ET. The problem with that is that there are residual methods, meaning that the water use is based on what's left over after you subtract all the measurements. What that means is that if you have any error, the error is added to your estimate. So here is eddy covariance. I've kind of tried to explain this over a number of years and slides, but I mention it again because I'd like people to really understand what's going on, and one level of complexity is it's really difficult physics. Another level, it's not that complicated. So this is my effort to simplify a complicated technique. The instrument on the picture on the left is what we put out on nearly 100 places throughout Yuma Valley. You can see all the sensors on there. There's air temperature humidity, which is on every weather station, a rain gauge, the net radiation sensor. Well, they have pyronometers on ASMAT, but not net radiometers. The critical components are what we call CO2 and H2O analyzers. Those are the ones that measure at 20 hertz. But what's really going on? To measure with this technique, we're trying to measure everything in that blue box. And we subtract everything that leaves the blue box, we add anything that goes into the blue box, and we need to account for anything that's stored in the blue box. So it's just inputs and outputs. Anything that comes in from the side goes back out the other side, so that'll be wind. We don't worry about that stuff. What we care about is the influence of radiation coming from above, which would be solar radiation and thermal radiation, so sky temperature. But some of it goes through the box into the soil, and so we've got to subtract out that soil flux. But then the soil puts some energy back into the plants, so you add that back in. So when you add up all the inputs and outputs, you get the equation down the bottom, which consists of 6 terms. The ones we can kind of neglect are what we call DQ and F. DQ is just stored, energy stored, and change in energy stored by the plant. But the biomass storage is pretty small, so we don't need to worry about that on a 24-hour. F is photosynthesis. Well, obviously there's photosynthesis going on, but in terms of energy contribution, it's quite small. So we're left with four terms: net radiation soil heat flux, which we measure with that net radiometer and soil heat flux plates. H and LE we measure with the sonic transducer. And that's it. So I'm trying to simplify a complicated process, but hope that I made it a little more clear on what we do. We also measure soil moisture. I don't know where Robbie is. Every year I get Robbie asking me a question about soil. Why don't you talk about soils? She's not here today, but we measure the soil moisture at shallow levels, and this graph shows that. We also measure the canopy temperature, which some people use to identify crop water stress. That's what we get here. This is just to illustrate that it's all in our data collection. So we're supposed to admit where the method falls apart, because no method is perfect. Well, to me, these are the biggest shortcomings for eddy covariance. One is what we call energy balance closure. So that equation I showed you before, when you add everything up, it should come to zero when you observe the sign convention. All the inputs should balance the outputs. And if they don't come to zero, well, you can say you're screwed, but you can also say there's some errors I haven't accounted for. That is called energy balance closure. And the way we analyze that energy balance closure is a plot that you see on the left-hand side. On the x-axis is what we call available energy from radiation. So we add up all the energy over the course of the day coming from the sun and from long-wave radiation, thermal radiation. We add all that up, put that over here, and then we add up all the turbulent fluxes, all the stuff that's measured by the covariance sensor. We add that all up, and we plot them x, y. So everything is perfect. They should all lie in a one-to-one line, but they never do. If we've applied all the corrections, we should have an r squared close to 1, and the slope, which I have here is b1, should be very close to 1. And when it's off from 1, that means you have some unaccounted for energy. So when we report the numbers in that report that you read, what's happened? How do we resolve, how do we reconcile the discrepancy between errors that we know about and the numbers? Well, I guess you could say it's kind of sweeping dust on the carpet, but we force energy closure because we know you can't have unexplained energy losses. And so the way we close those is that we use the Bowen ratio, which I showed you earlier. A second Achilles heel to this method is called flux footprint. So the thing about those other techniques when you measure water use, you know that that's the water that was used at that spot. You took a soil core, you know that's what was water consumed. But we're trying to get the water consumed for 40 acres or whatever the deployment is. And so this method relies on the direction the wind is coming from, which is all directions. So we strategically locate these eddy covariance stations so that we not so that most of the time the wind is blowing over your crop of interest. But there are some physics problems, and that is related to the atmospheric stability, the wind speed, the measurement height, the crop height. And if they are wrong and your field is too small, what's called flux footprint goes outside of your field. This plot here illustrates flux footprint for a lettuce field. You can see the red shows you the 90%, it's like, actually that's 50% of the flux footprint. It means that what you measure comes from that red area. And the outermost blue shows you where you know the energy is coming from, 90% of that. So a lot of times if you look at eddy covariance study for water consumptive use, they don't give you that flux footprint. They're not really revealing all the information you need to know, because if that flux footprint goes outside of the field boundaries for a lot of the times, it means the numbers don't mean what you think they do. So we pay attention to that for all the crops. And sometimes we find bad results, and we have to report that. Now, in the end, after all that long-winded description, what do the water use looks like on a daily time step? And here's an example from lettuce. It just shows you from October to nearly the end of December, and the black curve, that's the daily water use. and I'd say very accurate. You can see where the irrigation events, for example, the sprinkler irrigation and the green at the bottom, corresponds very well to the Y water use. And then there's a stage 1 of drying. And then there's another irrigation event. These blue lines are subsequent irrigations. And then the evapotranspiration spikes up. The correlation is excellent. We know we're measuring something that makes sense. We irrigate, we get higher water use. But we're actually measuring the amount. It's not just a binary thing. If there's irrigation, it's more humid. The red curve shows you the reference of evapotranspiration. Well, why do we care about that? Because we use the reference of evapotranspiration to scale estimates of water use when we don't have eddy covariance data. So we want to know, what would you estimate if you didn't have this expensive station? What are we doing now? Well, the report had to go out before we finished alfalfa or citrus. So I'll have a couple of slides on that. We're working crop coefficients and heat units. The crop coefficients is near and dear to the Bureau of Reclamation. They've been a major funder. Whether any grower uses crop coefficients is kind of a mystery to me. Maybe somebody here can help me with that. I think not very many, but I think it's a good tool for some crops. And the reclamation, it's very important to them for their water use. So we will work on that. The tools will be discussed a little bit later in the second speaker. So we will complete the crop coefficient study this year using satellite data. We'll use data from all 6 irrigation districts, not just Yuma. We'll use satellite data. And the thing is, since I started, especially the European Space Agency has provided satellite data free of charge that gives images of Yuma every 3 to 5 days. So this is pretty amazing because now you have resolutions around 30 feet. You can see what's growing in every field nearly daily. Less important to producers, of course, are peer-reviewed. You know, that white paper has been locally reviewed, but peer-reviewed by some critical reviewers somewhere else in the world. They're the bread and butter of my research life. And so we have that. We have that for the crop coefficient study, which is available free of charge for anybody who wants to download it. And our paper on lettuce, which I know is an important crop in Yuma Valley, was just accepted for publication 2 days ago, so that will also be available for anybody who wishes to see that. They can see some of the details I presented to you here. We'll continue the external collaboration, obviously locally here and with USDA and Maricopa, and to some extent that NASA is willing, we'll have collaboration with them. The last step mentioned here, data collection curation. It's like, this is kind of boring librarian kinds of stuff, but it was a lot of work to collect this and we don't want to lose it. And so we're working hard to not only just store the data, but include the metadata so anybody looks at it knows how to access it and what it means. Alfalfa, yeah, the big water user, I'm not telling you anything you don't know, but it's a difficult crop to analyze because of the major crop heights and logistics, and sometimes we have to move the eddy covariance stations multiple times. So here's an examples in the upper left showing you the daily variation, which is in blue, and the red is the reference of evapotranspiration. You can see that there's big changes between reference evapotranspiration and the actual evapotranspiration. And in the summertime is where your water saving opportunity lies, but there's still a lot of water used during the summer. The deployment illustration there in the middle, on the upper right shows you what satellite data look like. So we have some actual data on the ground, and we have data from satellite data that can give us the biomass. On the lower right shows you a comparison study that Dr. Sanchez has worked on a lot, which is a comparison with drip irrigation and flood irrigation, and there's some differences that he may want to discuss. Just to promote our accuracy, we are measuring irrigation volumes with acoustic sounders, so it's not just a crude estimate of flow velocities and cross sections. We also use volumetric measurements from acoustic sensors, and also supplementing our data with drone observations to get fractional cover. Citrus is a similar experiment. Much more difficult to measure open soil evaporation, so we're using sap flow gauges, which have been used for decades. We've deployed that so we can get transpiration. University of Arizona has a unique tool that you might want to know about. It's a LiDAR drone. There are not a lot of them around, but it can measure crop height and give you stupendous resolution of canopy geometry, and that's in the lower middle. And the lower right shows you the LiDAR outcome. It shows the differences in tree heights. Very accurate. So if tree heights or canopy geometry is important to you, the university has a tool for that. I guess lastly, I have to watch my time. So we're looking at two techniques for estimating and predicting water use. One is heat units. Now, for some vegetable crops, heat units are kind of crummy, I think. I'm not supposed to use crummy, but anyway, they have their shortcomings in accuracies, right? But they're readily available. Everybody can get heat units. What we need to do is identify the upper and lower limits for the heat units, collect some data on it. We can know the uncertainty of it. And this is an example of some of the data that we're able to collect here in Arizona. Shows you the progression of heat units. The upper left-hand corner shows you a progression from day of planting to date of harvest, so we can collect the statistics on heat units. Heat units are correlated with reference evapotranspiration, although they're lagged by about 20 days. So if you have reference evapotranspiration, that's sort of a predictive element for growing degree days. So the current methodology of predicting water, in simplified terms, is this: to integrate remote sensing and heat units. We use historical climatological heat units. Arizona, ASMET has 20 years plus of weather data, which is a great collection. We use satellites to do three things. We find out when the irrigation event occurs. Of course, growers know exactly when they irrigate, so we don't need to tell them anything. But for the rest of us who are not part of that, if we want to know, we need to figure out when to start the modeling. And that upper right-hand corner shows you multispectral data from satellites that can pick up the first irrigation events and maybe subsequent irrigation events. The third piece to the puzzle is figuring out when do the plants emerge. And that's kind of hard because the plants are so small and your satellite resolution isn't, maybe it's 30 feet or something like that. But there are spectral indices you can use. We're using what's called a red edge spectral indices, and it's able to pick for lettuce in case emergence in about 20 days with pretty good accuracy. Fourth part is fractional vegetation cover, which drives how much water you use in your model. Again, there's no soil in any of this, right? But anyway, fractional cover can be estimated using another spectral indices. When we put these together, we have a step 5, which is a crop growth model. In this model, you start on the left-hand side and work your way to the right. So on the left-hand side, it's like, this is the beginning of the season. How much water am I going to use by the end of the season? Well, you're not there yet, so you don't know. We're trying to figure out, what are the bounds? What's the minimum amount of water you can expect to use, and what's the maximum? And what's the most likely? The black is the most likely. And our current models show you that the black is awfully close to the final, which means, in a way, that you can toss away all these complicated models and say, I'm planning on September 15th, how much you're going to know within 10 or 15% of how much water you use if you follow traditional cropping practices. But the thing about remote sensing is it doesn't just give you a statistical basis, it gives you an actual observation. So you know precisely when the plants emerge, not when it statistically emerged, and you know precisely when the crop reach maturity, and that's based on observations. So there's good opportunity for using such data and integrating them with heat unit models. The last plot that I showed you is blown up just to show you that there's sort of discontinuities in that prediction model. That's because of satellite data. So you're going along and you don't know when you're getting an observation. When you get it, you've got to update it. It's going to give you a discontinuity in your estimate of crop water use. I mean, you could go back and roll back the whole estimate and recompute it. That's not how this model works, but that would be an improvement. On the left-hand side is a web-based application. Maybe Toby will talk about it on Talk 3. But it's a tool available to you right now on the web. You can look at it. You can use azimuth stations, and you can plug in your heat units, your minimum, maximum, and your threshold for maturity, whatever threshold you use, and it'll predict date to maturity. Manuscripts, I think I already mentioned. It's our bread and butter in the research world. Most of you don't care maybe about that, except that you do care that the data are validated and somebody else has blessed them, right? So if it's passed through peer review, it means you can probably trust it. And we've got a lot of manuscripts. Data collection, I mentioned that. We're putting a lot of effort in it because there's terabytes of data that have been collected. So they'll stop here and say, look, what have we done? Well, we have this report, which I hope some of you are interested in looking at. Dr. Sanchez really saved my career by bringing him in 2016, and I'm really grateful for that collaboration. And now we have almost 100 eddy covariance deployment sites, 14 crops, validated crop water use, ancillary things that he'll discuss with the salt salinity studies, and they've been published, so we're pretty happy about that. And the path forward is to finish up alfalfa citrus and see what we can do about predicting crop water use. And that's it. Thank you very much.
From year to year, is going to be tremendous variation from your published results then? I mean, you showed back to those early USDA.
I don't think so. I think the results that we have are going to be pretty stable. What's different is the way the farms were managed in 1962 is not the same as you manage it now. But as long as you keep your runs the same, that you compact the furrows, you start with sprinkler irrigation and you change to, in the case of lettuce, if your farm management practices are the same, and the crop varieties, of course, they'll change a little bit, I don't think you'll find a lot of change. That's my speculation. Maybe you disagree. I don't know. I think those are pretty good numbers.
Now, one caveat, Andy didn't show you the data, but he has modeled data for 20 years based on the azimuth database, and it clearly shows the trend of global warming. And lettuce is maturing in a lot shorter time today than it did 20 years ago. So there'll be those kinds of nuances to climate.
Well, there will be.
So you can estimate the heat units are going to go up year by year? Is that because of the global warming?
Yeah.
They have gone up.
Well, that graph I showed you shows you what the azimuth stations have seen. And there's some jiggle, right? But clearly in 2003 they were down here, in 2020 they're up here. It's an integrative thing. So like day to day, that year might have been a little warmer, a little cooler, but it integrates all of that, and there's a trend. Yeah, it's a pretty clear trend in heat units.
Could you make a prediction for a 10-year?
Well, that I'm not predicting that. So
When I was asked to put this project together over 8 years ago, I recognized I didn't have all the skill sets needed. And I started to poke around, and I found out the guy that had everything I needed, who had an office and a lab a block away from me. So I went and found him, and he's really filled the gaps and what we needed in delivery of this project. Okay, I'm going to talk about salt balance, and Andy's talked about crop consumptive use and ET, but we got to keep in mind that there are other non-consumptive beneficial uses of water that we can't ignore. And I've made a list here: climate modification, land preparation, residue, decomposition. Sometimes our irrigation system is less than perfect, so we have to compensate for distribution non-uniformities. But what I'm going to address today, it's of paramount importance to sustainability, is salt management. And it's kind of unfortunate that I have to do this, because it's been a recognized risk for a long time. That's what prompted the government to set up the Salinity Laboratory in Riverside to develop tools so people can manage salt. And I was surprised about 4 years ago when I would meet with water managers and hydrologists. They thought the potential conservation savings was simply where you are today minus ET. And that really puts us in a bad situation and at risk. So I want to talk about salt management. I'm going to define it, and then I'm going to format this presentation a little differently than I have in the past. I'm going to cover the present and existing challenges and give some real-world data to show you something. First of all, the major effect of salt is osmotic stress. Plants have to expend energy to draw water against this osmotic gradient, and that's energy that they divert from growth and reproductive processes. That's the major effect of salinity, regardless of the cation or anion. And we quantify that with different measures of electrical conductivity. Most of our reference standards are based on a saturated paste extract, but we have tools to go into the soil and measure bulk conductance, and I'll talk about some of those. And of course, we monitor the electrical conductivity of irrigation water directly. Conductance in the field. I showed this earlier today with respect to variable rate nitrogen management, but there's some different kinds of instruments. The first one is the Virus. That's an instrument that a service provider might use. The second one is an EM38. That's a research grade instrument, and that's what we use because it gives us a better integration through the profile for measuring conductance on a spatial basis. Talking about salinity, these are the anions and cations we're talking about in the river or in any irrigation water source, and you can see the approximately 2.5-fold increase from irrigation water to soil water. Your soil water has those concentrations, and from my own databases, I kind of showed the ranges you can find depending on management. Now, salinity risks to plants are all defined using this Mass-Hoffman approach. You have a level, salts will increase, it has no adverse impact, then at some threshold, it begins to have an impact, and that impact has a characteristic slope. This is the one for lettuce. Lettuce has a threshold of 1.3 decisiemens per meter, and it has a slope of decline once you pass the threshold of 13%. This is just an example. Every crop has a characteristic relationship such as this. You will see this one again in the context of some of our measured data here very shortly. How do you manage salts? You manage salts by leaching. You have to add extra water to move the salts below the rooting profile. This is based on steady state mass balance. Steady state mass balance is a simplification. It's oversimplification, but we do not have the databases to drive transient models, which take into account precipitation, dissolution. I have done a lot of transient modeling, but as a practitioner, to make recommendations over a wide range of soil types, we really don't have that. So we're using steady state mass balance. It's a little conservative, but that's all we have, and it's not that far off in a situation like ours where we farm year-round. This just shows different leaching fractions depending on the salinity concentration of the irrigation water. This depends on the water, and this depends on the characteristic susceptibility for crops, and this is just exemplifies the relationship. I mentioned transient models. This is why we would use transient models, because carbonate chemistry in a system, some of these salts can precipitate, but some of these precipitates can and redissolve, and we have models that can deal with this, but typically over a wide range of soil types, I do not have the Gapone exchange constants or some of the hydraulic conductivity coefficients to drive these more complicated models. But I also want to mention something else about carbonate chemistry. If you precipitate calcium with carbonates, it can increase the risk of sodium. And I'm going to say something about sodium here in a minute. But I just want to say we've run some of our soil solutions through our models, and we do exceed the KSP of several mineral species. So I don't wish, by using steady state, I don't wish to ignore the reality that we are getting precipitation and dissolution. I just recognizing the reality that I do not have the tools to use transient models as a practitioner. Sodium, that's a different deal altogether. That's a unique subset of salt risk. It's not an osmotic effect. Sodium destroys soil structure. There's no question about it. You can use the adjusted SAR, which takes into account the propensity of carbonates in your water to precipitate calcium. I like what's called the cation ratio of structural stability. It recognizes the reality the magnesium is not as equal a flocculator to calcium, and it weights it appropriately, and it recognizes that although potassium is not the deflocculator, sodium it is one that nonetheless needs to be taken into account. And a lot of the waters I'm encountering, now that there is an increased use of groundwater in central Arizona, is very high in magnesium. If you're just using this, you're underestimating the sodium risk. But sodium can totally destroy soil structure, and the first steps are reductions in infiltration. First subtle, then extreme. And I'm going to show this figure again in the context of some data we've collected. So the first challenge is salt management challenges are going to increase. In a drier climate, they're going to increase for other reasons. And I'll share some Bureau of Reclamation data with you. It's not my data. Since 1974, they've been mitigating the salt content of the river. They've plugged up saline seeps up in the northern basin. They've lined canals to reduce runoff through saline subsurface media. They've done lots of things. And you can see they decreased the salinity loads of the river at different monitoring points, Hoover, Parker, Imperial. And they've done a good job. But they themselves do not anticipate that they continue this. One, there's the uncertainties of climate change. Two, this is dependent on a congressional budget allocation. And they may get an allocation, they may not. It's probably not going to increase. And what something bought in 1974 does not buy the same in 2024. So as far as projecting with their models, most of their models show a lot of variation depending on what scenario they assume, and none of them have it going down even further. Most of them have our salinity challenges in the river increasing as we move into the next 2 or 3 decades. The second point I want to make is improvements in irrigation efficiency improve your need to conscientiously manage salts. This is where we are in Yuma. This is where we've been for 2 decades. In central Arizona, the state of Arizona is subsidizing improvements in irrigation efficiency. They're buying people-centered pivots and linears and drip systems. These are systems that weren't efficient. Long runs, high intake soils. Their soil management was incidental to their inefficiencies. Their leaching fraction was just part of their inefficiency. Now they're going to have to consciously manage salts. And you can see here in Yuma, we're irrigating so efficiently, salts increase over a cropping system. This is lettuce in the YD. You can see the salts increased across the fields. We know this. Our growers know this. As long as they don't increase to a point where it's catastrophic in that season, they're okay with that because that enables them to manage their nitrogen more efficiently. They're not leaching out their nitrogen. It enables them to not leach out their soil insecticides like imidacloprid or their herbicides like Curb or Prefar. This is environmentally sound. Push your leaching fraction off season. We can go through other crops. This is wheat. I used to assume, 9 years ago, I would have told you we get our leaching fraction, much of it in a wheat system. We're irrigating in basins, friction losses as water advances low. No, we're not. We're irrigating wheat as efficiently as we are lettuce. We're accumulating salts during wheat. We're accumulating salts through many of our rotations in the system. This is a lettuce-wheat system. You can see pre-irrigation, we took it down. It increases for lettuce, and then our salts increase again for wheat. This is what we have to mitigate with our midsummer pre-irrigation. It's of paramount importance to sustainability. We can go across different systems. This is lettuce, watermelons. Salinity increased during our lettuce cropping season. It increased during watermelons. We got to take care of that before we go back into lettuce. And you can look at all the crops. Andy mentioned all the crops we looked at. We looked at salt bands as well in these same systems. And you can see most of the time over our cropping season, we had a net salt increase. This isn't sustainable without that leaching irrigation in the summer. So we go back to this figure I started out with that shows the Mass-Hoffman criteria for defining risk. And this is from our data. This is the average on my lettuce watermelon systems. This is the average on my lettuce Sudan systems. This is the average of my lettuce fallow systems. This is the average of our lettuce wheat systems. We are clearly at an area where lettuce yields would be compromised if we don't do that summer irrigation and restore salt balance. There's no question about it. And that's measured data. Now, we want to do this well, okay? We know we have to pre-irrigate in the summer. Do we put 12 inches on? Do we put 4 inches on? We want to put enough so that we are sustainable, but we don't want to put so much that we waste water. And as we developed an irrigation app that Andy mentioned, and the final speaker is going to demonstrate for you, we wanted to give you a tool to track this leaching requirement deficit. So you might use it to irrigate, you might not, but you put your data in, and it'll tell you your leaching requirement deficit over the season, and it'll tell you exactly how much water you have to put on to restore salt balance. No irrigation management app had ever done this, and we thought this was very important for sustainability because it gives us a tool to do this and do it well, do it based on science, not guessing. Okay, I'll run 10 hours on there, or, so we can tell you how much water, how much of a hit to put on to restore salt balance. The other thing that we have to recognize is loss of surface water allocations will result in increased use of groundwater. This has happened in central Arizona. I've seen it happen over the past 3 years. Interestingly, the Bureau of Reclamation has been snooping around looking at groundwater sources around here. Their thought was if surface waters became short, they might augment supplies with groundwater. The problem is almost all our groundwaters, not all of them, but almost all of them in Arizona, at least in the central part and the western part, are inferior quality to the Colorado River surface water. Here's some data I have from central Arizona. This is what they used to divert at Brady Pump Station. Very good quality water. It's better quality than we divert at Imperial because we get return flows from Palo Verde and Crit. This is before the river, the surface water is impaired from these return flows. Very good quality water. These are some ranges of surface wells, what they call source wells, that Katy will use or that Maricopa Stanford Irrigation District will use. You can see clearly they're going to have challenges. They're going to have challenges in salt management, and they're going to have, worst of all, sodium problems. They're going to have to proactively start using water treatments and soil amendments to keep these soils sustainable because this water is clearly problematic relative to Colorado River water. I only mention this kind of as a case study because the Bureau has indeed done surveys here and has contemplated using groundwater to supplement our surface water locally in the event we do reach a crisis, but there are risks. Here's the Colorado River. This is my data. We're right on the edge. We're okay. Colorado River takes drainage through gypsiferous shells. Therefore, the calcium to sodium ratio is pretty good. Now, if there's less runoff in the future, we have more impact of some of those ugly tributaries like the Virgin or the Dirty Devil or the Paria. This could shift up and we could have problems. We might have to proactively manage for sodium, but we're not there today. We do not have to manage for sodium with the existing situation in the Colorado River water, and that's measured data. Let's look at Pinal County. Let's look at the MSIDD wells and the Katy wells. Create a lot of problems. There's just no question they're going to have to use water treatments and soil amendments to evade sodium problems. Now, that's an interesting area. The growers there now are going to have to relearn what their grandfathers knew. Before they got the CAP, they had to deal with this kind of water. They haven't dealt with it for 2 or 3 decades. They're going to have to relearn what their grandfather once knew and manage against the sodium risk. The last point I want to make is, and Andy touched on it, you've got to consider other consequences when you make a decision. And one of those is fallowing. At least in the riparian districts, which is much of the Yuma County area, even if there's no crop, we saw evaporation. This isn't ET, there was no crop. Andy, we put eddy covariance systems, and you still continue to get evaporation. Water continued to fluxes up from the water table. And And that shallow water is much more saline than surface water. You can see the increase in salinity. This is over a summer fallow period. Quite substantial increases, really, over this entire field that was in that summer fallow set-aside program. So I guess my only point is, I don't want to say fallow is bad because there's lots of good things to fallow. I think we got to weigh all factors and decide what the best plausible outcome is. Now, the shallow groundwater is also poses sodium risk. Sodium is more mobile than calcium. Sodium will move down. The shallow groundwater does not have the favorable calcium to sodium ratio that Colorado River water does. So even after this fallowing period, you can see we're getting into problematic levels of sodium that might cause us some infiltration issues. And this is something we have to contemplate. So to summarize what I've said today, collecting all this data over the past 8 years and looking to the future and looking at some of the challenges I see today and some of those coming on the horizon. First of all, irrigation efficiencies are high, and there's just no question we don't achieve salt balance within our cropping season. And that's a good thing, I consider. We're not leaching nitrogen to the groundwater like we did if we applied a leaching fraction offset. We're not leaching out our curb or our imidacloprid. This is a good thing, but we have to deal with that salt after the cropping season has passed. Efficiencies are going to go up across the state. I see it in Arizona. I see center pivots going in. I see linears going in. And a lot of these systems, there was no consciousness given to salt. Their salt management was incidental to their inefficiencies. That's not the case now. With a pivot or a linear, they can apply water directly at ET replacement. And they're going to have to consciously manage salts. And because some of those groundwaters, they're present much greater sodium risk than the Colorado River, they're going to have to consciously manage sodium, which is not the same thing as salinity. It's a unique subset of salinity. There's no question that summer pre-irrigation is of paramount importance to sustainability. I'll die on this hill. And the other thing is, and the last speaker is going to touch about some of the things we have coming out of cyber technology, is some of these tools we're developing. And we are proud of the desert-wide app because it'll enable us to know that salt balance deficit irrigation that we need. That's all I have. I'll answer any questions if anyone has any. Yes, sir.
So with the U of A grant program asking for 20% water reduction, is that not counteractive to?
No, that we want to have that 20% water reduction where it's possible, which is long half-mile fields on coarse textured soils in Arizona. That's a good thing. My only thing is when you go there, they're going to have to remain cognizant of the need for salt balance. When I used to meet with hydrologists with CAP, I used to get frustrated because they think your potential savings is simply where you are today minus ET. That's not the case. We're not sustainable if we get salted out. And so a lot of lessons that we knew a century ago are going to have to be relearned by some sectors of our community. Anything else? Yes, sir.
You mentioned nitrogen. You know, in California with the SGMA and the implementation in the Central Coast, it's all about reducing nitrates in the groundwater. And it seems like a whole lot of it is just due to inefficient irrigation, too much nitrogen leaching. When you're pre-season leaching here, how does that impact the nitrate levels in the soil, and or is it, the practice is better here or different here?
It's not necessarily better, but what's happened, and I've showed data on this morning, our nitrogen sold in Yuma County has dropped by half over the past 15 years. Our growers are improving nitrogen use efficiency. Unfortunately, for those on the BART area, we are not where we need to be for California's water quality control mandate. We have to get to an A-R of 50. We have 10 years to get there, but we're not there today. But no, we're not where we are in nitrogen, where we are with water. Water, we're incredibly efficient. Nitrogen, we're probably only about 60% efficient. But we've come a long way in 15 years. So we can get there, but whether you leach in season or you leach after season, at night, if there's nitrate in the profile, it is going to move. Right. Yes, sir.
Why is it that sometimes EC increases in like near surface soils after leaching? I think you had a graph that showed it increased after leaching.
No, the one I showed for the wheat lettuce rotation, it decreased on the surface, but it increased in the subsurface. It pushed it down.
Okay, because I've seen the opposite. I have a study from Snyder Ranch, we're at JV Farms, and we actually saw an increase in EC after leaching, and sodium was the only one that didn't go down. I didn't know if...
that would be atypical unless it was very hot in the summer and they didn't leach very much and all the water was evaporated.
Yeah, that's what I could see with flood, that you actually get some...
So you can dream up a plausible scenario where that would happen, but if your pre-irrigation is correct, that shouldn't happen.
Okay.
Yes, sir.
The displacement with gypsum, for example, if your pre-plant leaching needs to have calcium present, right? Gypsum.
We don't have that problem because the Colorado River water is essentially liquid gypsum. Now, if you're talking about some of those source wells in the Maricopa-Stanfield Irrigation District, they could use gypsum, or they could use sulfuric acid, or they could use elemental sulfur, but they will have to manage for sodium.
But not just leaching by itself. It's got to be some displaced.
Well, that's what impairs infiltration, is the sodium. It destroys the soil structure. So you need a flocculated soil to preserve infiltration, and that's what the gypsum does. But bear in mind this, and I've seen people make this mistake, gypsum itself is a salt. It's a neutral salt. So you've got to be careful where you use it and how you use it and how much you apply. And sometimes it's better to make that gypsum application outside the salt-sensitive crop, because gypsum is a salt. It's a neutral salt, but it's a salt nonetheless. So while the calcium's good, if you have a sodium problem, it is a salt. So bear that in mind when it's deployed as a management tool. In contrast, elemental sulfur uses your calcium carbonate in your soil to make gypsum. The sulfur is oxidized, it makes sulfuric acid. Sulfuric acid reacts with calcium carbonate, and it makes calcium sulfate. That's just microbially dependent, so there's a time lag.
Counterproductive.
What?
It's counterproductive?
No, there's just a time lag. You have to take into account that it's a microbially mediated process, and you've got to account for that time lag. So if you go down in November and put elemental sulfur, don't anticipate that's going to happen over the winter. No. Yeah. Okay, well, thank you.
It's always tough for me to follow Dr. French and Dr. Sanchez because they're such comfortable experts. Me, on the other hand, I'm just a bit head. I'm a computer nerd. My name is Toby Torrey, Director of Web Development for the Arizona Experiment Station's Communications and Cyber Technology Department. I'm just a computer person, so if I stumble and misuse growing terminology or say something nonsensical about planting a certain crop in the wrong time of the year, please forgive me in advance. Here I go. So we are here to talk today about Desert AgWise. We were contracted, not sure how many years the eddy covariance stations were being used, but somewhere in the middle of that, they brought us on to think about how to best deliver the data that's coming out of this research, but also to think about how we can interface these models, the science, the data with actual growers, actual growing data, and hopefully provide a two-way street to improve both our science and growing conditions. It's based on ASMET, and like Dr. Sanchez was saying, it's one of the first, if not the first app to provide this insight into the leaching requirement during the growing season, but also in between crops as you're planning for pre-irrigation and such. The models were developed and maintained by USDA ARS and U of A researchers. And right now the app is live and working for wheat, lettuce, and cotton. We're just now publishing, maybe even like right now as we're speaking, publishing the kind of the last few improvements to the lettuce model that we're making. And we have a slew of improvements to the cotton model slated for development right away after the lettuce model. So I expect these will be ready very soon. These improvements were hinted at a little earlier. We developed cotton first using time of the year instead of heat units as kind of the underlying metronome for a lot of the plant's aspects. But we've adapted it to heat unit and found it's working better across Yuma, across Arizona, and across different planting dates. So we're hoping to bring, and we also applied a similar logic to lettuce, but the cotton one will follow right after. So today, I want to share my screen and walk you through Desert Ag Wise, show you what it does, what you can use it to do, and what it's asking of you. If you can see my app, here it is. This is a local dev version. So it might not be exactly what you see if you go to desertagwise.org. I believe the developers are actually publishing some fixes right before this presentation, which makes me super nervous, of course. But they're good improvements and something that we're continuously doing. So once you log in, the idea is that the application helps you manage, let's say, what we call multiple farms, one or more of your farms. So if you were to create a farm, you can then place one or more fields on that farm. And then on each of those fields, you can place one or more crops. And I'll show you what that looks like and what that means. Farm is really just a... Right now, there's not too many properties associated with the farm. It's kind of like a folder that holds multiple fields. But within this farm, I can add a field. So let's add a field. And the first thing we're asking, is to draw the location of your field. If it's a simple rectangle, there's a rectangle tool. There's also polygon tools and circular tools. And it starts pulling some information, the latitude and longitude of the center point, the acreage, and it starts doing some auto fetching of soil type based on, it checks with an NRCS database based on the latitude and longitude, and it averages a few different soil types or soil depths together. So it might not be perfect. So if you know better than our assumption based on that lookup, you're welcome to override this with what's more appropriate. We name the field. Then we pick the azimuth station that you want to use for all of the weather data that's goes into calculating the irrigation recommendations in the Salinity insight. Presumably, it's the nearest azimuth station, so you would pick that. Then you tell us a little bit about your initial soil salinity, since this is your first time signing up with this tool for this field, and then the water source. Every time you irrigate, you'll be able to tell us whether you used a different water source, but here's where you get to tell us what your default watering source is. And let's say it's not Colorado River water, it's some kind of treated water all the time, or you're fertigating and you know your EC. This is where you would tell us the salinity of the input water. So let's go back to Colorado River water. All right, and then we talk about the first crop we're adding onto this field. So each field can hold one crop at a time, and we expect that the field will host one crop, and then there'll be some in between the harvest. After the harvest, there'll be some time for fallow or pre-irrigation or whatnot, and then there will be another crop in the future. So the field is kind of a perpetual place for all of your crops, and I think I'll touch on that a little later about the main improvements we're working on right now. But here you would tell us what the crop you're growing is, whether you irrigate it up or not, the planting date. So let's say we planted November 16th, projected harvest date. The projected harvest date doesn't affect any calculations. It's really just a quality of life thing that give you a heads up, and it's something that can be adjusted a little later. But planting date is critical to our calculations. And then your default irrigation system. So again, every time you irrigate, you'll have the opportunity to tell us how you irrigated, and this will affect our irrigation recommendations because some of these methods have different efficiencies and such. And again, I apologize if I'm picking nonsensical choices, but here I go. I'm going to save this field and success. So now we've created a new field, and presumably we want to tell the system that we irrigated on the planting date. That would probably be useful to tell. So let's say I did that with 1/2 inch of Colorado River water, the irrigation event. And then here you would see all of your fields, and you can zoom in on one individual field here. I'm going to do a quick refresh because I noticed there's this add field button bug here. Goes away on refresh. And this is kind of your dashboard for the field. Since you just created this field and the planting date was some time ago, we're going to tell you that ASMET detected 13 different rain events rainfall events since planting date till today. And we're going to do the calculations for irrigation recommendations based on the ASMET rain, but of course you might have the opportunity to confirm or deny that it actually rained that much, and you'll be able to edit them as well and adjust them if you have your own rain gauges locally. And on this history tab, which you can view as either a list form or as a calendar form, this is where you would manage your water events, as we call them. So if it rained on your field and ASMET did not detect it, you could tell us a little bit about that. So you can tell us that it rained so much, and you can make some qualitative notes for future reference if needed. But the other thing that we expect you to provide is irrigation information. So this app altogether, one of the things it's asking of the user to provide is irrigation amount. So if this is somewhere, an area of this tool that we can improve, since it's so important to get this information from the user, this is where I would love more feedback for future improvements. But here you would tell us when you irrigated, how you irrigated, how much you irrigated. We're working on some cool calculators here or converters in case you don't know right away how many inches you applied, but you know in some other metric what you applied, and we could convert that to inches based on the acreage possibly, and the type of water, and then you would add these irrigation events. And as you add those irrigation events back on the summary, it would affect what's labeled leaching shortage here and the projected irrigation for the next day that we expect you to water and the amount of inches to water. I'm seeing that is nonsensical now, so I wonder if my inputs were strange. It says my next watering is December 30th, 0 inches. So we'll have to look into that. But the leaching shortage might be better phrased as leaching requirement, leaching deficit. This is what Dr. Sanchez was talking about in terms of this is the amount of water you'd be expected to apply to balance out the salinity. And this is based on the crop's salt tolerance, the chart that he showed where after a certain threshold, it starts affecting that crop. But we don't necessarily expect the user to act on this information during the growing season, but that it's more of an insight. So if this number starts growing out of control, it might affect decisions during the growing season, but more likely it's something to keep an eye on during the growing season, but to then manage in between growing seasons. So again, we also have some cumulative deep percolation, and since this is the dev version, we have some dev data output coming out. I do want to talk about and some opportunity to reset some of the information you told us before. So that's a quick glance at what the tool looks like, what crops it works for, and how to use it. But I do want to spend some time talking about what we're actively working on right now, and upcoming improvements that we have slated, but we could always use some feedback to help us prioritize these upcoming features. And ultimately, the tool is configurable so that people like Dr. Sanchez and Dr. French, they can go in and adjust the default salinity of Colorado River water, for example. I didn't know Colorado River was projected to get so salty, but we'll need to adjust things like that. And as we have better understandings of the salt tolerance of crops, we can feed those in, and also irrigation methods and the efficiencies of those and how the soil impacts all of that. All of these factors are knobs and dials that are exposed to the researchers so that they can tweak them without the computer guys in between. Active and planned development. So I've hinted at this a little bit, and this is something the previous presentations have hopefully underscored, is that the management of your soil, of the salinity in your soil, doesn't stop and start with the crops and the growing seasons. And in fact, you probably know way better than I do that a lot of that's managed in between growing seasons with pre-irrigations and such. When we built this tool, this app, we really focused on how it behaves and the inputs and outputs and the intuitiveness for during a growing season. But the more our team interacted with the researchers and the more we understood the practical application of the science, the more it became clear that the interface really needs to be intuitive in between growing seasons, and also almost perpetually or cyclically within one field across multiple crops. And I think that's kind of the last bullet point I put on this slide, is a tool that lets you split and merge subsections of fields on a kind of a schedule, so that if one field, the whole thing is wheat, but then after the wheat is harvested, it's split into vegetables and something else, and lettuce or something. But then it always goes back to wheat on a predictable pattern. Maybe that's something that's worth encoding into the application, because right now it's just a single shape and a single crop for that shape. So again, we're researching and we're designing right now, and we will begin development of these improvements of in between growing seasons. Another improvement that some research indicated might be critical to adoption. And again, this is the main goal of any improvement. And my philosophy, or our team's philosophy, is to lower the barrier to adoption. So if anybody here has any feedback on anything I've already shown or anything I'm about to talk about, and you know that a particular improvement would lower the barrier to adoption for you, I would be very keen to hear that so that we can prioritize accordingly. So let me get back to sharing contributors. This would be a way for users of the app to delegate either a farm or a field to somebody else, so that maybe an organization or a team might be able to all work together on one field or a collection of fields for a farm. And that could be configured. We could build that very granularly, so that this grower can only do X, Y, and Z, but does not have permission to do A, B, and C. So there's a lot of opportunity there, but we're waiting to determine maybe a potential partner that would be a key improvement for their opportunity to adopt. If they didn't have that, maybe it wouldn't be usable for them. So that's something I'm keen to understand as well. And then the next 3 points are moves we are making already. So you can expect them to be available this year. The web API access to irrigation and salinity models. We built all of the science and the models in a way so that other people and other applications can tap into them. Right now, they're locked down so that only our application can access it, but we would love to find opportunities to understand how somebody else might want to connect with it and how they would deliver their data and how they'd expect the data to be delivered back, and then determine if some authentication is necessary for security reasons or data privacy reasons. And to facilitate that, we likely need the ability to import large chunks of data. If you start using the app in the middle of a growing season and you have 10 fields, it might not be practical to go in and add all these past irrigations that you already have in a spreadsheet. So we're actively developing a CSV importer. We're starting with a template that we're defining, but again, if we can find some partners or some core user group that can guide us on how the data is already formatted or the data structure or the software that it's already in, all of that could inform us on better ways to import. Then I have here a containerized application for local deployment. This is something we're not actively developing right now, but we are looking to pivot in this direction. Right now, the application lives on our cloud infrastructure, and it interacts with the API that we built. But we could, in theory, containerize both the application and the API so that it can be installed locally on your infrastructure, and then your data can feed it and get recommendations out of it without your data ever leaving your ecosystem, in theory. This will be great for any user who has lots of weather data that they would prefer to use instead of ASMET, but that they can't legally, expose by uploading to some other website. That's the need we're anticipating by putting this on the list of future improvements to plan. And then again, as you've seen, a lot of opportunities to improve the quality of our recommendations, to improve these water models for these crops by incorporating more or better satellite data as we have better understandings of how different spectra affect the growth of different crops. I expect that researchers like Dr. French will be able to improve the model on the condition that we can use satellite data as an additional input. And that's something we've also heard in some brief research from potential partners, is that their weather data that they have is either supported or comes from satellite data that they pay private organizations to access. So this is something that we'd like to review, but right now I think our priority is growing in between seasons and the web API, kind of the interactability of these models so that it can serve more than just this one application. And then I mentioned the scheduled splitting, merging subsections of fields. So this is the active and planned development for our team in the experiment station. So our coders have this on their ticketing systems, but I can also reiterate or clarify that there are planned developments for more crops, and I think that's something that we would depend on Dr. French and Dr. Sanchez for, is as we're happy with wheat, cotton, and lettuce, we can look ahead to several vegetable crops that they've suggested are just about ready to incorporate, and look forward to future crops and determine what we need in order to incorporate crops like alfalfa. Okay, so that is Desert AgWise, the app where you log in, you tell us a little bit about where you are, your soil, you tell us a lot about your irrigation, And then we tell you what the expected water use should be and what the salinity is looking like in your soil, what the buildup might look like. But we're also putting together a set of references for crop coefficients, as Dr. French referenced a little earlier. I'm not an expert on how these will be used, so it's a little harder for me to imagine the typical user that comes to this tool or comes to these references. But as I understand more and more, we're refining this, and we're about to launch an entirely new web experience, a website for the Yuma Center for Excellence in Desert Agriculture, and that will include what I'm about to show you, an improved version of what I'm about to show you. But this is, I'm going to open this up in another tab and share that screen. Water use and management section on the Desert Ag Solutions website, desertagsolutions.org. There's some breakdown on water use, on growing degree days, and heat units. Also, vegetative indexes like NDVI, and a salt management through leaching. Little review of some of what you heard today from Dr. French and Dr. Sanchez. But in addition to that, we want to provide, and we will soon launch all of these, provide per crop breakdowns of growth stage versus GDD versus NDVI versus crop coefficient. So you can see through the growing season how these change. In addition to this, so this reference is not going to look the same for every crop, as I understand it, since some crops are better understood than others. Some crops just have more discrete stages than others. But this is a reference that is open to anybody, that doesn't have to log in. You don't have to tell us anything about your field. And the other tool that's paired with this is something Dr. French showed a little screenshot of a little earlier. And this other tool is the Arizona Heat Unit Calculator. And this is what I imagine. We're going to pair this calculator with each of these crops like that we list here, so that if I go to wheat and I want to use the calculator for wheat, there'll be a button to do so. But it would take you to this calculator, and there would also be a cheat sheet here in case you need to look it up, like what is the base, what is the max that we use for calculating wheat, and then what is the base and what is the max for a variety of crops, so that you can use these kind of with our guidance, or you can use them to your heart's content to calculate at what point, how many days into a season, if I planted on a given date, let's say I planted October 20th, really long growing season, Yuma Valley, and here's it's configured for a particular crop. I want to know at what point do I hit a given GDD. So if I know, that I'm going to be harvesting at 1250, or I should be expecting to harvest or seeing the first node at a particular GDD, this will estimate for you. The green line being observed data from this past year, from ASMET, and then this orange line being predicted data past today for, just zoomed out when I did it. But the orange line would be predictive based on averages, historical normals on ASMET. And this would take you to determining on what date should you expect to hit that GDD. So we think that this will be a tool that will probably have some overlapping use case with the full Desert AgWise app. But for the most part, I imagine this will be a separate use case where a grower or a researcher has a lot of information and just needs the last few pieces and can put that together here without needing to upload a spreadsheet of all of their past irrigations. So go back to the slide. Right. So again, yeah, all those parameters can be overridden for a custom calculation of accumulated heat units. Okay, so that's all I pretty much had to show today. I have a shameless plug slide that I'm just going to show but not talk too much about, but we are the experiment station. If you don't know about us, the Arizona Experiment Station is made up of facilities across Safford, Yuma. We've got ranches up in Yavapai, Maricopa, on campus and around campus. And CCT, we're the cyber infrastructure arm of that experiment station so that we can support instruction, we can support extension, we can support research like we're doing for Dr. French and Dr. Sanchez. But we do so through development of applications, hosting of applications, and all sorts of complex cyber infrastructure that's needed to support these efforts. So just a little spiel about who I am, who I work for, and how we came to partner with Dr. French and Dr. Sanchez, for which I'm very grateful. So that's all I have for today.
So one is I wondered about plants, like if there's any like cropping rotations that could potentially like cover crops that could potentially accumulate salts. I mean, we're talking about salt mitigation. What happened? How do we manage salts with less water? I guess besides desalination, which we know is very expensive. And, so that's one question. The other I want you to think about is I can't help but notice a lot of our salt experts at the U of A are retired or close to retired. Jim Walworth, Jeff Silvertooth, you, Dr. French, who are you passing the baton to? I mean, as you know, as things move forward, we have these huge challenges that you showed. So how do we, is it a new position that you imagine?
Well, I talked to John about this. We lobbied for that soil health specialist position, but I told John we also need a soil scientist skewed towards the physical and chemical sciences.
Yeah.
Like me.
Right.
And I don't know where they are on that. That's not my call.
And it seems like it's hard because I'm trying to find salt experts, and you're like my main go-to.
But yeah, I talked to them. I told them we need someone a little stronger in the physical sciences out here, and we'll have to see how that plays out. Those decisions are made at a different pay grade than mine.
Yeah, yeah. And what about the plants, like in terms of?
Well, there are known plants that mitigate salt, but again, it's always tempered by the economic equation.
Yeah.
The growers want to rotate with things that either are at minimal risk or maybe a small profit margin, and you just can't go out and lose $500 per acre on a summer crop.
Mm.
Although Sudan grass is probably about losing about $200. Okay, any other questions? But yeah, you're probably the best lobby for another physical scientist.
Yeah, we need that person.
Hey, Dr. Sanchez, I have a question.
Yes.
I was thinking about the leaching requirement, the leaching deficit, and how it's tied to a particular crop's sensitivity or tolerance.
Okay, we've talked about that. In Yuma, they would almost always have to use the sensitivity for lettuce.
Okay.
Because almost every piece of land ends up in lettuce within a 2-year period, and most of it always every year. So even if you're going to grow broccoli or this or that, land still needs to be ready for lettuce.
That answers my question perfectly, because I was wondering in between growing seasons.
So like if you're in Central Arizona and you're growing cotton, then you would type in the tolerance for cotton. But if you're in Yuma, you almost always type in the tolerance for lettuce, because you use the tolerance, use the sensitivity of the most sensitive crop in your rotation.
Okay, thank you.
Does that answer your question?
Perfectly. Yeah, before I even asked it. Perfect. Thank you.
Okay, thank you all for coming. These afternoon sessions are tough, but we got a good audience.